All right, this is part 2 of chapter 9, and really I shouldn't be saying graphing polynomials. It should be rational equations or rational functions. We can call them either or. All right, polynomials, we can't have a fraction in a polynomial like how we're going to have here. So we have a couple new pieces that we're going to need to know before we graph these. Starting off, we talk about points of discontinuity. Right, and points of discontinuity are like the excluded values, right? They're the excluded values from last last chapter, right? For what we're going to be doing, it will always be where the denominator is 0, right? Anywhere the denominator is 0. Within the realm of discontinuity or points of discontinuity, we're going to have two types. We're going to have holes and we're going to have vertical asymptotes. A hole is what it sounds like. It'll be like a graph, maybe it's a line and it's just kind of going along and then there's a little bitty jump. Okay. An asymptote is going to be a vertical line. I normally do a little dotted line. And the graph can't touch and it can't cross that line. Normally with an asymptote, it'll do something like where it's coming down and then it just zoops down. Something like that. So remember how in the last chapter we would start off by factoring everything and then we would try to cancel, right? We'd factor everything, we'd list our excluded values, and then we'd try to cancel. Holes happen when the discontinuity cancels. Okay. And then vertical asymptotes happens when the discontinuity doesn't cancel. So what does that mean? If we were given the equation, let's say x over x plus 1, right? It's already factored for us. We know that there is points of discontinuity at 0 and -1, right? We have 0 because of this x, and then we have -1 because this guy. Now we can cancel, and we'll be left with 1 over x plus 1. So the 0 canceled. So this one would have a hole at x is 0. But then the -1 stays, so it would have a vertical asymptote at x is -1. Okay, so that's what we're going to be doing there. And then we also need to talk about the other kind of asymptote, and we're going to call them end behavior asymptotes. End behavior asymptotes. Okay. Sometimes these are called horizontal asymptotes. Actually, most of the time they are called that. The reason that we're calling them end behavior is because sometimes horizontal asymptotes break the rule of asymptotes and you end up being able to cross it, which an asymptote you can't cross, but an end behavior asymptote you can, which is kind of weird, and we'll get to some of those later in the packet. For this, we're going to have two situations on our notes, or on our work. There are other situations that are out there, but we're only going to deal with two of them for now. So starting off, number 1, we'll say the degree of the numerator is bigger than degree denominator. Okay. Whenever the degree of the numerator is bigger than the degree of the denominator, we have no asymptote. So what would that mean? Degree, if we remember, degree talks about the exponent, the biggest exponent of a polynomial. So if we had something like, here's our fraction, we've got like x cubed plus x squared plus x, blah, blah, blah. Whereas the bottom one maybe is x squared plus x plus 5 or something like that, you know. The top's degree is 3, the bottom's degree is 2, right? We only care about the highest exponent. In this one here, the degree of the numerator is 3, the degree of the denominator is 2. 3 is bigger than 2, so we have no asymptote. Okay. Now the other situation is where we're going to have an asymptote. Number 2, we're going to say the other situation we'll have is degree, let me change to blue, degree numerator is going to be equal to degree denominator. This one means that there will be a asymptote at, and it's best to just show an example of this. Say we have an equation like 5x cubed plus blah, and maybe 2x cubed plus blah, right? It doesn't matter that they're cubed, it matters that they're the same, right? So they could both be to the 5th or something like that. What we do here is we look at the leading coefficients, the 5 and the 2. This one will have a horizontal asymptote at y, or excuse me, an in behavior asymptote at y is 5 over 2. Okay. The first few problems don't have that, so we don't have to worry about that quite yet, but we need to make sure that we have these pieces written down somewhere that we can remember these. We're going to need other things, but these are the only new things. So let's look down here. We have to identify the holes, vertical asymptote, X-intercepts, horizontal asymptote, or in behavior asymptote, and the domain. And then after we do all that, we're going to sketch the graph. Okay. Now, it's tempting to just type these into a graphing calculator, and eventually we will do that. But to begin with, I want us to sketch them by hand and be able to learn what they generally would look like, right? We'll check all of our answers with a grapher, okay? Speaking of graphers, I'm happy with you guys using Desmos on your phone for homework. I don't want you using Desmos on the test, okay? So you'll need to get a graphing calculator, or let me know and you can borrow one of mine. But yeah, I don't really want you using your phone on the test. So starting off, I'm going to list the domain. Well, actually, you know what? Starting off, I'm going to factor. The top I can pull an x out of, so x minus 3. The bottom I'm going to pull a negative 3 out of. Negative 3, x minus 1. So let's talk about domain. The domain is going to be all reals, given that x won't be 1, right? Because that's our excluded value. Nothing here will cancel. So talking about holes, we have none. Vertical asymptote. We are going to have a vertical asymptote at x equals 1. And I'm going to go ahead and sketch that in here. So x equals 1. I always like to do little dash lines. Now the asymptote isn't actually a part of the graph, right? If we were to just graph the graph, the asymptote won't be there, but the asymptote is useful when graphing. Like by hand, it's useful. If you type this into a grapher, it will not show the asymptote though, because it's not technically a part of the graph. What's up next? I guess we'll talk about end behavior asymptote. I'll just say end asymptote. Well, this one here, we need to look at the original. The top one has a degree of 2. The bottom has a degree of 1. So we have none. Now for x-intercepts. X-intercepts, you say you want y to be 0, right? Because x-intercepts always happen on the x-axis where it's not shifted up, not shifted down, y is 0. So really we want to set this guy equal to 0. And the only way that that can happen is if the numerator is 0. Right? So instead of looking at the denominator being 0, now we look at the numerator being 0. To get the numerator to be 0, it would be 0 and 3. If we were to write this as a point, it would be 0, 0, and 3, 0. Okay? I'm okay with you just listing the x values, like how I have here. I'm not okay with you saying this, because 0, 3 is not on the x-axis. So you can't say that. You could put the comma there even, but you can't put the parentheses around it and list it as a point, right? Because that would be incorrect. All right. I'm going to graph my x-intercepts at 0 and then at 3. And now we've exhausted everything that we can. We don't know what else to do. There's nothing else that we have to find. So what we're going to do is we're going to go back to a t-chart. X, Y. And whenever you're deciding things to plug in, there's no necessarily correct answer, but you want something to the left of everything and then in the middle of each piece. Okay? So what I'm going to do is I'm going to use -2, -2, 1/2, 2, and then we'll use number 4. Right? So -2 is to the left of everything, 1/2 is between the point and the asymptote, 2 is between the asymptote and the point, and then 4 is to the right of everything. Right? So if you were doing this on your own, you'd have to stop and, let me see if I can erase these. You'd have to stop and plug all these in. So you might want to pause and just see if you get the correct answers. But this is what I got whenever I plugged them in earlier. I got 10/9, -5/6, 2/3, and -4/9. Now, I don't care if you leave them as fractions or if you leave them as decimals. It really doesn't matter to me at all. This is just what the calculator spit out at me. So -2, 10/9 is just going to be a little bit bigger than 1. 1/2, -5/6 is a little bit less than 1. 2 and then 2/3, something like this. 4, -4/9 will be something like that. So it looks like generally what the graph is going to do will be something like this, right? Remember how it always does that funkiness where it just falls down or it rises up near an asymptote. Something generally like that. Now that we've sketched it by hand, let's look and see what it would actually be. So this is going to be x squared minus 3x, and then -3x plus 3. So here's what it would look like. We can see that we have the vertical asymptote at 1, and it does kind of the swoopiness near the asymptote. So that's that. It looks pretty similar to what we have, which is good. Let's look at another one. Number 3 here. Let me talk about this a little bit more. The graph, it's much, I don't want to say difficult, much more difficult. It's different typing it into a real graphing calculator, right? So if you plan on using a graphing calculator on the test, which I would suggest it, you should be studying and you should be doing your homework with it too. Okay, it's very different. There's not a good way for me to pull up a graph or on the videos though, so I can't do that. Number 3. We're going to start off by factoring everything, so we'll pull the x out, then we'll have x squared minus 6x plus 8. On the bottom, I can pull a 4 out, so I'll have 4x squared minus 2x minus 3. The top will factor to x minus 4, x minus 2. The bottom will factor to x minus 3, x plus 1. Domain will be all reals, given that x won't be -1 or 3. What was the next thing that I always find? Wholes. Can anything cancel? The answer is no, so none. Vertical asymptotes. We need to list all the excluded values that were not canceled. So that's all of them. So this will be x is -1, x is 3. Let's go ahead and graph those on our graph. All right, next up after vertical asymptotes, we need to talk about end asymptotes. For the end asymptotes, we start back at the beginning. We have an x cubed on top and an x squared on bottom. So this has none. For x-intercepts, we will have an x-intercept. Remember, we need to look at what would make the top 0. So that'll be 0, 2, and 4. 0, 2, and 4. All right, we've done everything that we can. Now, again, we need to do a t-chart. So I'll say x, y. Looking here on the left side of the asymptote, we don't really know what's going to happen there. So I'm going to plug in 2 different things into our chart. So I'll plug in -6 and -2. And then we'll plug in -0.5, 1, 2.5, 3.5, and 6. Okay. Now again, I grabbed 2 from the left side there, 1 from right in there, 1 from in there, 1 from in there, 1 from in there, and 1 from right there. All right, whenever I type these in, I got -8/3, -12/5, 0.8, -3/16, 0.27, -0.29, and 4/7. All right, we need to sketch these roughly. -8/3 is going to be, what is that? Almost 3. What is that? 2 2/3. So -6, 2 2/3 will be somewhere right in that region. -2, -12/5 is going to be, what is that? -2 2/5. So something like that. -1/2 0.8 will be somewhere right in, positive 0.8. Something right in there. Then we'll have something there. Something in that region. Something right there. And something in that region. From this, what it looks like to me is there's going to be a little bit of a parabola in the middle here. The right side here looks like it's going to swoop like that. The left side, though, I don't really know what it's going to do. I look here, and I kind of want to say that it's going to do this. But I know that if it were to do that and hit the x-axis, we would have had it marked already. So what I'm going to do is I'm going to plug in another point. I'm going to plug in -1.5. And whenever I plug that in, I get -3.2. So that's all the way down here. So that helps me know what's going to happen. It's going to do a swoop down. So that's that. And let's actually graph with a grapher now and see how close we are. We have x cubed, minus 6x plus 8x. And then we have 4x squared minus 8x minus 12. Did I mess up somewhere? Oops, this should be a squared there. There it is. All right, and there we are. It looks pretty close to what we've got. It's not a perfect parabola in the middle, whereas mine looks kind of perfect, but it has that general U shape, right? So there's that. All right, I'm going to finish the video now. Make sure again that, I mean, it's great to use Desmos. It's a great tool. Make sure you're using it after you try the problem. Otherwise, you don't actually get any practice at it. And if you plan on using a grapher on the test, which I would expect you to, I would say that you should probably be using that now. So, all right, that's that.